G'day team, welcome back to yet another video on the introduction to differential calculus. In the previous video we looked at some different types of rates of change, but overall we were doing the same thing. We were looking at the gradient of a line. Now our final thing we looked at was instantaneous rates of change, which was finding the gradient of a tangent at a specific point. Now that leads us into today's video. Now, we know we need 2 points to calculate a gradient. Now, if I wanted you to find the instantaneous rate of change at point A, we now know we draw a tangent, so I've got that orange tangent there, and we find the slope or the gradient of that line. Now, this one here, this tangent is very tricky because there's no nice points along that tangent. But the second thing we looked at yesterday was, what if we find the average rate of change between 2 points? That we would know how to do. So let's introduce a point B, and we could find the average rate of change there. But we can see that these slopes aren't quite even. So what can we do to fix that? Now, I've got point A here, and then I've got point B, which is just some distance h from point A. So we've called that A plus h, and it's separated by h. But what happens when we can bring this h value and make it smaller? So if I say A plus h is now here instead, that means I've got my B value here. So let's draw a tangent there. Now we can see this new tangent line in here is actually, it's starting to look a bit closer to the same gradient as I've got at the tangent of A. But what if I bring that h value in even further and I make my B value here now? And I draw a tangent to there and I zoom in a little bit. We can see that it's actually getting closer and closer to the gradient at the tangent at point big A. Now, we're still calculating a gradient between 2 points. So we've still got my change in y over my change in x. Now, the y coordinate for this B point is f of a plus h, and the y coordinate for my big A point is f of a. So I've got f of a plus h minus f of a. The x coordinate is a plus h, and I'm subtracting a. Now those a's can cancel out, and I'm just left with h on the bottom. Now this is just the gradient of this line between A and my new point big B. It just looks a bit funky, okay? And like I said, to calculate the gradient of the tangent at A, we're going to move that point B really, really close to A. So that means that distance between my x points, my change in x or h, becomes really, really small. Now, as we move that B closer and closer to A, this is the idea that we call a limit. Okay, so it's almost like a converging point. So if we can make f of x, our function, as close as we like to a real point A by making x sufficiently close to little a. So x is any value of x, and a is my specific value. So then we can say f of x has a limit of big A, my y value, as x approaches a. So the way we write this is the limit as x goes to some known x value of my function, okay, on my function, then it equals this big A value, and this is often just the y coordinate at that point. And like I said, we can also say that f of x converges to A as x approaches little a. But keep in mind, we're not actually looking at when x is equal to A. We're looking at what happens when it gets really, really, really close to A. All right. Now, we're going to practice doing some limits. Now, I want to make a little note here. So if x is in the denominator and it cannot be cancelled to 1, i.e. we have 1 over x, then the limit as x tends to 0 of 1 over x does not exist, because at x equals 0, this is undefined. So that's a little rule we're going to keep in mind when we're going through these questions. So the limit as x tends to 3, okay, so that's my specific x value of x squared plus 1. Now, because if I apply my limit and I look at what happens when x is equal to 3, my function exists, I can substitute in 3 for x. And it looks like I'm just doing a substitution, but I'm applying the limit. Now, 3 squared is 9, so I've got 9 plus 1, so I've got 10. So the limit as x approaches 3 of x squared plus 1 is 10. Let's have a look at b. The limit as x tends to 0 of 3 over x. Now, if I apply the limit, I've got 3 divided by 0, which is undefined. Okay. Therefore, the limit as x tends to 0 of 3 over x does not exist. Okay, so because we can't play around with anything, we can only substitute in 0. It doesn't work because it will become undefined, does not exist. Now, if I'm looking at this one at face value, if I put in x equals 3, I get a 0 on the bottom, which we run into the same problem here. But on the top, we have a little bit of a quadratic. Now, some of you may have spotted that that's a difference of 2 squares, and I can factorize that into x minus 3, x plus 3, all divided by x minus 3. Now, you should know how to cancel out factors, and I've got an x minus 3 on the top and an x minus 3 on the bottom, so that equals 1. So I'm just left with x plus 3. Okay, so actually I'm going to move that over a little bit because we haven't applied my limit yet, so I'm going to rewrite my limit. So the limit as x tends to 3. Now, if I do my limit, I can, because it doesn't make it undefined, so I get 6. All right, hopefully that helps a little bit with limits. We will expand on this in the next video when we look at some derivative functions and start getting into the nitty-gritty of calculus. Thanks for watching, and we'll see you next time.